Okay, so thanks also to Nick for the invitation to this workshop, which I think is coming along very nicely. I think the talk by Nicholas was great in introducing a bit where the people that come from imaging are trying to hit, which is trying to incorporate more physiological information into, let's say, the image analysis techniques and using the models also for having some predictive power. I hope I will convince you that although in some of the talks that we have been hearing these days, it looks that we have already solved a lot of problems. Actually, there is a lot of things still to be revisited and to be improved. So our work, especially or even in particularly in the geometric side, because unfortunately is ubiquitous in almost anything you want to do afterwards, that you need to have a segmentation. And I think there is still a lot of work to have proper tools there. So our work is also, as Nicolas mentioned, framed in the context of the European project, where we have a big team of groups there. Our work, or one of our tasks within this project, is actually developing tools for doing the anatomical reconstruction of the models. The framework that we are using for that is statistical models which have the advantages of providing a common coordinate system. I won't explain again something that probably some of you have heard in some of my previous talks about this Google Heart notion, where you want to actually map all the different information from the multiple modalities into the same coordinate system, but this is in a way core to that idea. We want to basically map the structural and functional information. We also want to have a compact representation of the average anatomy to know roughly what is the average heart, but also to understand and parameterize the variability that this morphology has over a population. And these also bring things about how to really automate and make robust the processing of huge databases. And if we have that, we can also have, through this parameter characterization of the morphodynamics of the heart, that will allow us to correlate the dynamics with other outcome variables or other type of information. The statistical shape models, I tried in this talk actually to provide a bit of a sort of tutorial, if you wish, to understand this for people who are not necessarily for the field. So we have basically three main components. There is a point, what we call a point distribution model, which is basically a statistical representation of the geometry without any intensity information. There is also what we call a statistical appearance model, which is how you endow this particular model with anything that has to do in which modality this was generated, whether it was a SPECT, a MR, CT, or for instance ultrasound. And then you have to have a final step, which is an algorithm as to how you take in this information into account, adapt this model to an image. So the first step is actually to construct this model. I'm not going to get in details into that, but you can refer to this paper, and we are actually now making an extension of that for full heart atlases, where basically the idea is that you define somehow a reference, and then you register a lot of cases that you have in a light database to that reference. You generate sort of the formation maps. Of course, you remove all the affine transformation, but you construct the formation maps. And from these deformation maps, you are able to propagate from basically this atlas landmass that you generated here and automatically landmark a large population. We are now developing models that contain over 1,500 volumes of data sets, and how to automate that, make it robust to failures, identify outliers, reject them, recompute. That's basically one of the main difficulties. So in the end, basically what you end up is having, say, 1,500 volumes of which you have a triangulation for all of them. But the good point is that all these triangulations have the same, have a consistency in landmarks between them, all of them. Landmark number 1 corresponds to the apex in all the 1,500 volumes, and so as for volume landmark number 2, and so on. So in a simplified manner in 2D, what you have is a database. This is just outlines of, let's say, supposedly a left ventricle, where for each of them you have a number of landmarks. And what you want to do is reconstruct an average model by averaging all these vectors, compute covariance metrics, do some dimensionality reduction, and generate basically a model in which the parameters of these models can be computed based on the average, the specific shape instance that you are considering, and a projection matrix that provides you the coefficients. So basically, this is the coordinates in, say, work coordinates, and you have these coefficients which are in the statistical space, or the principal component space. So if you map, these 1,500 volumes into the two main principal components, this may look like a sort of Gaussian cloud, and you can constrain the values of these coefficients in such a manner that any model you generate is falling within the statistics of your population. This allows you to determine which are valid shapes. So this is not a valid shape because it's outside the statistics. This is a valid shape. You can also get what is a closer shape. So if you have one that is not a valid one, you can get which is the closest valid one into your population. And also you can have a measure of representation error within your subspace. Now the good thing is that in this subspace it can be relatively reduced in size, so you can have on the order of 30,000 coordinates in the 3D model, but you can end up reducing that to about 60 variables in your principal components and have a reasonable accuracy. We have recently published also a technique for actually doing bilinear models, so we can not only model the morphology across individuals, but also we can model in a decoupled manner to the variability across individuals. We can model also the variability over time and have them as two different variables. So the model, these are the Bs that I was showing before, and you have a temporal component and a subject-related component. The good thing is that you can do very good extrapolations of the for left ventricle, and right ventricle, and full heart models, in which by only having, let's say, 1/3 of the data sets over the cardiac cycle, you can extrapolate for the other 2/3 with pretty good accuracy. Now, the other thing which is important is, so you have this statistical representation, but you want to have a way to then model the intensity statistics around every landmark, and you do that by modeling some sort of intensity information. Sometimes it can be the intensity directly, sometimes it's a gradient, sometimes there are other features from the image. Say, for simplicity, the intensity. So for every landmark, you create basically a profile that looks into the intensities underneath and uses that as a description of that location. And then in order to find the right location where a certain landmark has to be moved, what you do is a sort of match filter that searches along the normal to the surface. So this is your learn profile, which is here now overlaid. And then you do this matching around until you find the place where it matches the best. And that's the position that you consider your candidate position. And you do that for every point in your shape model until you have a candidate for every single location, and then you try to deform your model constrained by the statistics of your point distribution model. I'm not going to get into all the details, but we also developed an algorithm called SPASM that stands for Sparse Active Shape Models, that is able to handle sparsely sampled data sets, because let's say not all imaging modalities are like CT, where you basically have all the densely sampled volume. You also have ultrasound, where it's more beam or even some specific sequences within MR that can give you radial scanning. One point that important that I missed to mention at the beginning is that what we are trying to do is to develop a technique for extracting the morphology, which uses exactly the same algorithms irrespective of what is the imaging modality that you're trying to reconstruct. Because if you look at, for instance, commercial software, any of the imaging vendors has a different package to, even of the same brand, for segmenting ultrasound, for segmenting CT, for segmenting expect, and that gives some sort of bias, which is not due to the modality only, but also due to the method you use for reconstructing anatomy. So we wanted to have a technique that allows to do this sort of fitting to this sort of very sparse data. Okay, so this is more or less, I will come back to that, but this is our framework for developing applications with Cost Genius, and we are developing these tools so that we can actually fit these statistical models, in this case, to the 3D ultrasound. Now, the other thing we have been doing is actually, how you come to this. Normally, for generating this training set, you have to do manual segmentations. And if you're talking about doing 2,000 volumes, 3,000 volumes, forget about doing that manually, which is what everybody has been doing in publishing so far, based on 30, 40 data sets where you can cope with it. So what we are doing is, once we have this PDM, can we actually reuse it and simulate the image acquisition in such a way that we can construct automatically the appearance models? And this is something we published for SPECT recently, and we have a paper under revision now for using the same concept in 3D ultrasound. So the idea is that instead of building these appearance models directly by outlining manually images and then learn the profile, we actually instantiate this geometrical model, we simulate the image acquisition, and we then learn the intensity models from the simulated data. Now, can we do that? Is there good simulators? Well, the good news is that there is actually a lot of very good so simulators of the imaging physics for essentially all the key clinical modalities. And these are pretty actually advanced. So by combining the generative model of the geometry that we have with all this information that models the physics, we can actually do that. So we have done one specific study in nuclear medicine where we have generated what I call an e-population, where in this particular case we use 200 cases, but we can do that with any number you want. So we generated populations which are balanced in gender and in some of the key anatomical features that these sort of patients normally have. And there is a bunch of parameters that come from papers in the literature, clinical papers, that actually provide values for many of the parameters we need in the simulation to generate a population which is physiologically or anatomically realistic. Okay, so basically the algorithm is we generate the anatomy with our statistical model. We generate the projections, in this case from a SPECT. We generate the reconstructed images with any algorithm we want to do, in this case AWESOME or filter back projection, and then you learn the appearance from these simulated images. So these are just examples of what happens if you use simple models like a step edge or a gradient model compared to a simulated model. You have in yellow the manual segmentation in real clinical images, and in white the outline that you generate after feeding the model based on these simulated intensity profiles. And you see that it's quite a good correlation. We have done the same exercise on 3D ultrasound, comparing two different simulators, Field 2, which is the more involved one, and another one based on simpler correlation. And okay, this is a bit flashy. But this is basically how you can reconstruct the cardiac cycle on these sort of models in which we learn the intensity from simulated data and we fit to real clinical data. We have done also validation here, for instance, of volume in our segmentations compared to the ground truths that we had from manual measurements, and you see that is pretty good correlation. And we have also compared the manual errors. So the errors, if we would train the models with manually segmented data sets compared to the errors we have when we use either one type of simulator or the other type of simulator for the same modality. And you see that actually the difference are really not statistically significant. We are talking about less than, say, 2.5 millimeters in ultrasound, which is not bad. Okay, if you want to actually have a look at these papers, we have done also a sort of a meta comparison to the literature, and what we observe is that the errors we are getting in terms of end-diastolic volume, end-systolic volume, ejection fraction, and absolute volumes are close to what is the intra and inter-observer variability that is in the literature, which I think is pretty good. So in conclusion, these population atlases, I think, help to have a coordinate system that where we can map information. I haven't really covered that aspect so much this time, but I show how you can use simulation as well for the imaging modality to actually completely automate the process of creating these statistical models. They provide a way to parameterize the anatomy and the dynamics of the anatomy. And we have shown a bit in two examples how we can develop model-to-image adaptation algorithms that are efficient and cross-modality. What are we doing at the moment? We are extending actually this to MR and CT. In MR, it has taken a bit more time because we have extended the simulator as well. I haven't shown it, although it's in the abstract, mentioned that we have applied the same sort of tools to fit to electrophysiology data. We have presented that in FIMH. So you can use the same statistical models even for things which are not, strictly speaking, an image. And finally, we are tooling basically all this into Genius, which is our application framework. And, well, if there is anyone that is interested in that, you can contact us. So, thanks, basically.
Thank you very much. So we have a question, probably just one short question, one answer.
Alex, that was very impressive indeed. How much progress have you made in being able to automatically generate models of the atria?
Okay, the models I show you in the segmentation are only left ventricle because the region of interest that you can see with those imaging modalities doesn't cover the atria. But actually, our 4D statistical model has whole heart, has the atria as well. So the thing is that you only see them in CT mostly or in MR. Sorry, in CT and MR. And we're actually in the process now of developing the fitting algorithms in those modalities. And we're actually now tackling how to segment atria. But I don't see it as a major item if we solve the other parts in those modalities that we're working on right now.
Well, thank you.